I don't think the microphone was on for the last tutorial. It's a big shame. That's okay though. Now it's a big time to get started. So how's everyone doing today? Doing good? It's very sad today's the last tutorial. But it's okay. We're going to make it a great last tutorial, okay? So before we get started, I do have an exit feedback form. I'm going to ask everyone, could you please fill it out. I'd love to hear all your constructive criticism, but also any positive feedback that you have will really help me. So please get a chance to fill it out. It'll be on the Academy page as well. So take 3 minutes whenever you get a chance. Now without, oh yes, question. Can you change my office hours so you can see me again? Like for next semester? Like next week. For next week? I don't even know if I'll be in there next week. I'm not sure. I still have to figure it out because some stuff to do with hours and stuff I filled in for some people early in the semester. We'll figure it out. We'll also talk at the end of the tutorial today. There might be some other stuff that I have announcements to mention. So we'll get to that. The feedback form is also posted on the classroom. Now we're gonna get started. Okay? So we're gonna get started with a U sub, and then we'll get into some other trig stuff questions before we finish. So let's talk about Olivia. How's it going? So Olivia loves potatoes. She cooks it anyway. And she has a theory that the tastiness of a potato dish is related to the angle that the potatoes are sliced. So Olivia sets up a model and finds that the optimal tastiness of a potato is given by this integral. So the question is, what is the optimal potato tastiness? So let's try and solve it. Let's take a look, okay? So if we want to find this integral, let's see. I think this cotangent part is really difficult to deal with. So let's see if we can simplify that a little bit. Let's remember that the cotangent of an angle is, that's cosine over sine, right? Yeah, it's tough to remember. Look to your formula sheet. So this will be equal to the integral from pi over 3 to pi over 6 of cosine of theta divided by sine of theta times the ln of the sine of theta d theta. Okay, cool. We'll try and use the u sub for this one. So maybe we'll try and let u is equal to the ln of sine of theta. Then du will be equal to 1 over sine of theta. But we also have to remember our chain rule. So the derivative of sine of theta, that's going to be cos of theta, d theta. Oh my gosh, that's exactly this. We have cosine of theta over sine of theta. So now let's make our u substitution here. So that'll be equal to, now we also have to remember to change the bounds. So when u is equal to, when x is equal to pi over 6, u is going to be equal to, we'll have ln of, now sine of pi over 6, that's 1/2, so we'll have ln of 1/2. And when x is pi over 3, then u will be equal to the ln of sine of pi over 3, so ln of root 3 over 2. So we'll have the ln of root 3 over 2 up to the ln of 1/2. We'll be integrating u du. So this will give us, we'll use our inverse power rule. We'll get 1/2 u squared evaluated at ln of root 3 over 2 up to ln of 1/2. So this will give us 1/2 times the ln of 1/2 squared minus the ln of root 3 over 2 squared. Cool. So if we take a look at our experiment results here, if we were to put this into a calculator, this will give us that the optimal tastiness is approximately 0.24, I believe. That's good to know. I don't know what that means on the potato scale. Olivia, what's your favorite way to eat potatoes?
Hash browns.
Hash browns? That's a great choice. All right. So is everyone okay with that example? Okay, do you have any questions about this? Because that was a really good question asked in the previous tutorial. Let's see if that comes up. I've got a question. Why are the bounds small? Why is the bound that's bigger on the bottom? Why is the bound that's bigger on the bottom? Right? Does that make sense? Let's actually remember that's actually okay, right? Even though it's convention to put the smaller bound on the bottom, all that happens is when you switch the bounds, the integral is off by a negative sign. So the integral from a to b of f of x dx, that's the same thing as the negative integral from a to b, from b to a of f of x dx. Yes, question?
Can we solve it without doing, like if I just switch the bound and made it negative, is that also considered correct?
Yeah, it would be considered correct. When you end up switching the bounds, all that will end up happening is that these two things will subtract off to each other in the other way, in the other order. So that's why it's only off by one negative sign. Good question. Any other questions? All right, well, thanks, Olivia, for the insights. We're going to get into some partial fractions here. Now, in class, I think a lot of the stuff that we've done on partial fractions, it seems like a whole mumbo jumbo of just divide by, multiply by terms, stuff like that all over the place. And I think that's really, really complicated. So we're going to get into the idea of what partial fraction decomposition actually is and why we want to do it. But before we do that, I'm going to ask you a seemingly unrelated question, okay? What if I wanted to add these two fractions? I want to add 1 over x minus 6, and I want to add 1 over 2 minus x. So I want you to add them. How are we going to add them? Yeah?
The same denominator.
Yeah, let's find a common denominator. Exactly. So what's going to happen is we're going to make a common denominator by multiplying. So we'll get 2 minus x divided by x minus 6 times 2 minus x plus x minus 6 divided by x minus 6 times 2 minus x. Exactly. And then we would turn them into a single fraction. It would all cancel. But basically the point is we would get one fraction. Partial fraction decomposition is like that process, but in reverse. It asks, we have one complex fraction, okay? We have some polynomial on the bottom with multiple factors. I want to turn that complex fraction into the sum of 1 divided by, or some number divided by a linear term, plus some other number divided by a linear term, plus some other number divided by a linear term. So what partial fraction decomposition says is, okay, I have this fraction right here that I want to integrate, but it's difficult to integrate that with that quadratic term in the denominator. So can we turn 4 divided by x minus 6 and x minus 2, can we turn that into some number divided by x minus 6 plus some number divided by x minus 2? Okay, we're going to take a really quick pause. Does everyone understand the goal that we just set up? The problem that we're trying to solve? Is that okay? We're trying to find some way to re-express this as this sum of number divided by linear factors, because those are really easy to integrate. So let's try and do it. So I think divided by quotients, that's really, really messy. So what I'm going to do is I'm going to multiply both sides by that denominator on the left. We'll multiply both sides by this. So we'll get 4 is equal to a times x minus 2 plus b times x minus 6. Okay, now we know that this equation is true for every single value of x. It's true for every single one. So now what I'm going to say is, okay, I want to try and simplify this equation and solve for a and b. And the way I'm going to do it is by using the fact that it holds for every value of x. So let's try and do this. We're going to say, okay, I want to solve for b. The way I want to solve for b is because a is unknown, let's use the fact that it holds for all x to try and get rid of that a term. So you see we have an x minus 2. I'm just going to set x to be equal to 2. We'll have 4 is equal to a times 2 minus 2 plus b times 2 minus 6. So that, look, that a term is going to disappear. This is just 0. So we'll get 4 is equal to negative 4 times b. So b is equal to negative 1. Great. So now what we know that that weight of the linear factor is negative 1. This is negative 1. Let's try and do the same thing to solve for a. So if we want to solve for a, we'll set x to be equal to 6 to eliminate this guy. We'll get that 4 is equal to a times 6 minus 2 plus b times, we have 6 minus 6. Notice our b term is going to go away. So we got 4 is equal to 4a. So a is equal to 1. So now that we have that this a term is weighted 1. So we just showed that this fraction can be written as 1 divided by x minus 6 plus, minus 1 divided by x minus 2. That's not so bad, right? And now we can try and integrate it. So let's try and integrate it here. We'll put that fraction over here. We just said that this big fraction here is equal to 1 over x minus 6 minus 1 over x minus 2. And now we can integrate it term by term. Now when we take this integral, we should remember that when we're integrating 1 over something, that'll give us not just ln of that something, but ln of the absolute value of that something. So this will give us this will give us ln of the absolute value of x minus 6 minus the ln of the absolute value of x minus 2 plus c. Awesome. Now, I had a question in the last tutorial about, okay, how can we just integrate that? Because don't we have to worry about the minus 6 and the minus 2? And you know what? That person is absolutely right. I skipped a step here. I actually skipped a u sub. The reason why we're able to skip this u sub is actually due to how nice the partial fraction decomposition is for us. The partial fraction decomposition is nice because each of these linear terms in the denominator, they're linear in x. Right? We have, if we were to do a u sub and we said u is x minus 6, then du is actually just equal to dx. So we don't really have to change anything. So this partial fraction decomposition is really, really handy. It lets us evaluate these tricky integrals in an easier way, and then we'll be able to actually do the integral in an easier way itself. Yes, question?
Would it be different for the bottom of the different x squared, plus 3x, if it was more complicated?
Absolutely. If the bottom it had some squares or it has some other factors. The thing is, with our partial fraction decomposition, we're trying to decompose our original rational function into the sum of something over a linear x term plus something over a linear x term.
So it's like you have a couple goals.
Exactly, that's our goal. Our goal is to try and make it as simple as possible. Great question. All right, so let's do another example here. Actually, you know what? I'm going to skip over this example just because we're going to try one that's a little bit more tricky. Feel free to evaluate this one. We're going to try this one here. Our goal is to find the integral of 1 divided by x times x plus 1 times x plus 2. And we'll try our partial fraction decomposition again, but this one's going to look a little bit more tricky. So our goal is to write 1 over x times x plus 1 times x plus 2 as the sum of a over x plus b over x plus 1 plus c over x plus 2. So our goal is, again, to write this as the sum of a bunch of weights over linear fraction. Okay? So we'll use the same process here. I'm going to multiply both sides by this big fraction here. So we'll be left with 1 is equal to a times x plus 1 times x plus 2 plus b times x plus 2 plus c times x plus 1. Cool. And now let's try and use these weights to the fact that we have a function x to try and eliminate all the other things so we can solve for each of those capital letters. So if we wanted to solve for a, let's try setting x is equal to 0. So we'll get 1 is equal to a times, we'll have 0 plus 1 times 0 plus 2. And you'll notice b and c, those terms will kaput, they'll go gone. So we'll have plus 0b plus 0c. This tells us that 2a is equal to 1, so a is equal to 1/2. All right, let's try and do the same thing. So we'll solve for b. So if we were to solve for b, let's try saying x is equal to -1. If we set x is equal to -1, that'll eliminate the a and the c terms. So we'll have 1 is equal to a times -1 plus 1 times x plus 2 plus b times -1 times -1 plus 2 plus c times -1 times -1 plus 1. So you'll see this is just 0. This is also just 0. So we'll say 1 is equal to, now b is -1 times 1, so 1 is negative b, so b is -1. So we'll try and do the same thing but for c. We'll just do one more of these. Hopefully it's not too tedious. So we'll solve for c. So to solve for c, we'll set x is equal to -2. So we'll have 1 is equal to a times 0 plus b times 0 plus c times -2 times -2 plus 1. So if we were to evaluate this here, this would give us that 1 is equal to 2c, so c is equal to 1/2. Cool. So we can take these weights that we just learned, and we can find that our original fraction can be written as 1/2, or 1 over 2x, minus 1 over x plus 1, plus 1 over 2 times x plus 2. Is that a bit small? Here, I'll zoom in a bit. So that's really awesome. We found a way to decompose our original very tricky fraction into a sum of much easier to work with fractions. So now that we have that decomposition here, I'm going to rewrite our integral. So this will be the integral from 3 to 5 of 1 over 2x minus 1 over x plus 1 plus 1 over 2x plus 2. So we've done these kinds of integrals before, so I'm going to speed through this one a little bit. We'll get 1/2 ln of the absolute value of x minus the ln of the absolute value of x plus 1 plus 1/2 times the ln of x plus 2. And you could evaluate this one from 3 to 5. And I'll let you verify the actual value of this one on your own time. Yes, question? Why is the second one a negative? Good question. So remember, our original weight for B was -1, right? So when I plugged it in up here, all I did was I made it cancel with the positive sign, so I put the negative there. Is that okay? Good question. Any other questions on that one? Awesome. We'll keep on checking through. Keep pushing through. Now, we've seen how to use partial fractions for integrals like this one, but partial fractions can also help us find difficult sums. So let's see if we can use this here. So it asks us to find the sum of 1 over n squared plus 3n plus 2. Let's try this. I'm going to rewrite the sum, and I'm going to factor the denominator. So we'll write this is going to be equal to 1 over n plus 1 times n plus 2. And we'll see if we can write this fraction as the sum of 1 over n plus something over n plus 1 plus something over n plus 2. So let's see if we can do that here. So we'll say our goal is to write 1 over n plus 1 times n plus 2 as a over n plus 1 plus b over n plus 2. So we'll try the same process again. We'll multiply both sides by the denominator on the left here. We'll have that 1 is equal to a times n plus 2, and we'll have b times n plus 1. We'll try and eliminate. So if we set n equal to, we'll solve for b. So if we set n equal to -2, we'll have 1 is equal to 0a plus b times, b times -2 plus 1. So we'll get b is equal to -1. And if we were to solve for a, that'll give us, if we choose n is equal to -1, then we'll get 1 is equal to a times -1 plus 2 plus b times 0. So a is equal to +1. So now we're okay with what we just did there. We said, okay, we'll try and represent this complex fraction as the sum of two other simpler fractions, and we found what those simpler fractions are. So we'll rewrite this sum. This is going to be the sum from n is equal to 0 up to infinity of 1 over n plus 1 minus 1 over n plus 2. Now, if you have a keen eye, you'll notice that our tricky sum now has turned into a sum that looks a little bit easier. Okay, what's special about this sum? There's a fancy name for it. Does anyone remember? Yeah. This is a telescoping sum. Yes, exactly. So what we can do here is we'll separate this sum term by term. N is equal to 0 to infinity of 1 over n plus 1 minus the sum from n is equal to 0 up to infinity of 1 over n plus 2. Now what I'm going to do is I'm going to change the bounds. So this n plus 1, I'll take the plus 1 away and I'll turn this into an n is equal to 1. I'll take the plus 2 away and turn this into an n is equal to 2. And you'll notice that'll just give us 1 over 1, which is 1. So you see how we can use partial fractions not only to simplify our integrations, but also as a tool that'll help us evaluate complex sums. Is everyone happy with that example? All right. We're going to skip over this next example because I don't really want to do it. But you can either, oh yeah, question.
Can you explain what you did at the end there with the changing the n?
Good point. Good question. So our first term of this one, here, I'll write what we just did, what we had earlier here. So we substituted this term by term. So we had n is equal to 0 to infinity of 1 over n plus 1 minus the sum from n is equal to 0 to infinity of 1 over n plus 2. So when n is equal to 0, so let's say we have the first term of this guy, right? N is equal to 0, the first term is 1 over 1, right? So we can do a change of the bounds by saying, okay, here the first term of 1 over n is when n is equal to 1. Did the same thing here. All we did was a phase shift. You might want to look back to our lecture or our tutorial notes from week 8. We did a couple more stuff on phase shifts. Good question. Yeah? The 1 divided by 1. So every term starting at 2 from this one will cancel with this one. Right? So that's why it's a telescoping sum. So the only thing we're left at is when 1 is equal to when n is equal to 1. Good question. We good with that example? All right, let's keep pushing forward. So for this one, you could just solve it using long division, or there's another nifty trick. I'm just going to cross it out for now, but I'll post the solution to this one in the classroom. All right, let's keep pushing forward. We're going to get to perhaps some stuff that might have been a bit more confusing. Trig substitutions. Now, these are a little bit tricky to remember, so I made a little nifty table for you guys. Now, you've probably seen the first three. Have you seen these last two, the hyperbolic subs in class? Who has seen them? No one. Okay, we're going to skip some stuff today then. You probably won't need to know it for the test, so don't worry about it if you haven't seen it in class yet. All we're going to do is worry about these first three trig substitutions, and we're going to take a look at integrals in these forms. So whenever you see a root of a squared minus x squared, we're going to make that substitution with sine theta. Whenever you see an a squared plus x squared, we'll make the substitution with tan theta. And when we see with x squared minus a squared, we'll use the secant squared substitution. And we'll use these nifty little trig identities to help us. Let me cross out these ones though. All right, let's take a look, shall we? So, now, originally what I wanted to do was, you can use these hyperbolic substitutions to solve some nifty problems. We were originally going to do an integral where we could do it two ways to show that these two things are equal to each other, which I think is really nifty. But now we can't do that because I was told not to do the hyperbolic subs, so we're not going to do this. Don't worry about it. And instead of in two different ways, in one way, we're going to find this integral. So you'll notice if we write this 9 as equal to 3 squared, so if I say this is the integral of 1 over x squared plus 3 squared dx, this is the same form as the tan integral. So we have the root of, if we have the root of x squared plus a squared, we're going to set x is equal to a tan of theta. So if we substitute this in, we'll say that this is the integral of 1 divided by the root of 3 tan theta squared plus 3 squared. Now normally we'd have a dx. I'm going to kind of wait till we have a theta here. So I'm just going to pause for a sec. This 3 tan theta squared and the 3 squared, let's actually take a look at this because we can do some clever manipulations. So when we have the root of 3 tan theta squared plus 3 squared, that's going to turn into the root of, we'll have 3 squared tan squared theta plus 3 squared. I'm going to factor this 3 squared and then pull it out of the root. So we'll be left with the root of 3 squared tan squared theta plus 1. So that'll be 3 times the root of tan squared theta plus 1. Now, what's tan squared theta plus 1? What's that? That's secant squared of theta, right? And if we root it, that's just going to give us 3 secant of theta. So this integral, that's going to be the same thing as the integral of 1 over 3 secant of theta. Now the thing is, we need a d theta still. So let's head back to our expression in terms of x. We'll find that dx is equal to 3 secant squared theta d theta. Let me just color this a different color here. So we'll substitute that back over here. We'll get 3 secant squared of theta d theta. And this looks like an integral that's a bit easier to solve. So after we compute this multiplication, our 3's will cancel, our secant squared will cancel with our secant, and we'll get the integral secant theta d theta. Now this is pretty tricky to solve. I think this might be on, oh yeah, question. This? So that came from, remember how we have a dx here? We have to substitute for the dx. So dx, when we have x is 3 tan of theta, then dx will be 3 secant squared of theta d theta. We just took the derivative. Is that okay? Awesome. Now, I don't know if you'll be expected to, I don't think you'll be expected to integrate this, but the integral of this, I'll just tell you, is the ln. All right, everyone. This is the ln of the secant of theta plus tan of theta d theta, plus c. And if you were to sub in a final answer, this will give us ln of the root of x squared plus 9 over 3 plus x over 3 plus c. A lot of people in the last tutorial, their question was, okay, how did we get this as the final answer when we sub back? We'll remember that x over 3, so if x is 3 tan theta, then x over 3 will be tan theta. So that's how we got the one on the right. That's how we got this x over 3. This root of x squared plus 9 over 3, this just came from manipulating triangles. So if you think back to our right triangle stuff, we can manipulate by finding the angle. We can say that our secant is our hypotenuse over our adjacent. And then once you do those manipulations, you can get to that answer. I think you guys can do that one on your own, though. So we'll move swiftly along. We're going to try this integral here. So this question asks, okay, what's the integral of 1 divided by the root of 1 minus x squared over 144? What we're going to do here is let's try this. I'm going to try and this might seem a little bit hand-wavy, but we're going to pull out a divided by 144 here. So we'll rewrite this as 1 divided by the square root of, we'll do 1 over 144 times 144 minus x squared dx. Is that okay? I'm just going to do that to try and simplify what we're doing. If you multiply it in, it should all be the same. Just think about multiplying it in. Once we do that, what I'm going to do is I'm going to pull the 1 over 44 is going to turn into a 1 out of 12 outside of the square root. And after you pull it all the way outside of the integral, it'll give you a 12. So this will be a 12 times the integral of 1 divided by, we have 12 squared minus x squared dx. All right, now let's think. What does this form look like? We've got an a squared minus x squared. Let's look all the way back up here to our table here. If we have an a squared minus x squared, that looks like this form right here. So we'll make the substitution x is equal to a sine of theta. We've got a lot of murmuring. I'm going to take a quick pause here. Do we have any questions about what we're doing so far? Any questions? It's okay. If you have a question while we're doing one, feel free to stop me anytime. So let's try and do this. We're going to make, oh yeah, question. The question's in the form of sine inverse. Let's see. Where, this one right here?
No, the question itself is the derivative of sine or arc sine.
This is the derivative of arc sine?
In the form of
It's similar, but we need to find out how to get there. Right? Let's see. So we'll make a substitution here. We'll set x is equal to 12 sine of theta. Then our dx will be 12 cosine of theta. And then also, let's take a look at what's inside the root when we take 12 squared minus 12 squared sine squared theta. That's going to turn into, we'll factor out the 12 squared. Oh, sorry, that'll be 12 squared times 1 minus sine squared theta. And that's equal to cos squared, 12 times cos squared theta. So we'll put that inside here. We'll get 12 times the integral of 1 divided by the root of, we'll have 12 squared cos squared theta. times our dx is going to turn into 12 cos theta d theta. All right, everyone. So we'll have this is going to turn into 12 times the integral of 1 over. We'll have 12 cos theta d theta divided by 12 cos theta. This is just 12 times the integral of d theta. So if we integrate that, that'll just give us 12 theta plus c. And if we substitute back in, since x is 12 sine of theta, that means theta is equal to x over 12, the arc sine of x over 12. So this is 12 times the arc sine of x over 12 plus c. Is everyone okay with that example? If you have a question, feel free. Yeah, questions?
Can this question also be done through substitution?
In a way, this is just like a U substitution. We're trying to do this one just because in the most recent child's math, this was supposed to touch on what trig subs look like. If you could do this with a U substitution, absolutely. We want to do integration. We can think of integration just as techniques that we're using to try and solve the problem. As opposed to with derivatives, we would just follow specific rules. Integrals, you can get kind of creative with how you solve them. They should give the same answer. Yes, question? Can we explain, with this 12 theta here? Right here? Very last step. All we did was we looked back to our substitution for x, and we isolated for theta. Does that make sense? All right, everyone. We're almost done. We've got some more questions to get through. This good in the back? All right. We're going to move swiftly along. I'm going to skip over this example. We've got just time for one more example here. Okay, I've got a question for you guys. Who's done arc length in class? Okay, who hasn't seen arc length yet? Oh, perfect. Okay, we had a decent portion in the last tutorial. So, in case you haven't seen it, all you need to know is that the arc length of a function is just that integral right there. So basically just find that integral. So for the very last question in tutorials this year, or this semester, the Math 1 T03 students, that's you guys, love candy canes. And the hook on a candy cane is given by, or is chased by the function y is equal to the root of 4 minus x squared on the interval 0 to 2. So it asks, what is the length of the candy cane? So let's try and solve it. So first, if we have y is equal to the root of 4 minus x squared, let's find y prime. So we'll say y prime is, now that'll be the same as 4 minus x squared to the power of 1/2. So y prime will be 1/2 times 4 minus x squared. Oh, all right, everyone, just 10 more minutes. We'll take 4 minus x squared to the negative 1/2. Times we need to multiply by our chain rule, so negative 2x. So if we were to rewrite it, that would turn into negative x divided by the root of 4 minus x squared. All right, everyone. So we'll use our arc length formula. So s will be the integral from 0 to 2 of the root of 1 plus negative x over the root of 4 minus x squared dx. We'll try and integrate this. So this will give us the integral from 0 to 2 of 1 plus, we'll get x squared over 4 minus x squared dx. Now what I'm going to do is I'm going to find a common denominator with this one. So we'll turn that 1 into 4 minus x squared divided by 4 minus x squared. You'll see that our x squareds cancel. So we'll be left with we'll have the integral from 0 to 2 of, now the top is going to be root 4, so I'm just going to turn that into a 2. So we'll have 2 over the root of 4 minus x squared dx. All right, now we're going to try and do a trig sub for this one. So what we're going to do is we're going to set x to be equal to, now we have an a squared minus x squared case. So we're going to set it to be arc sine. So we'll set x equal to 2 sine of theta. Then dx will be 2 cosine of theta, d theta. So if we rewrite this integral, that'll be the integral from 0. Actually, we're going to have to change the bounds. But it's okay. We'll just sub back in later. We'll have 2x. We'll have dx is going to be, so this will turn into 4 cosine of theta d theta. We'll have the integral of 4 minus, we'll have 2 squared, so 4 sine squared theta. Also, I'm sure you've seen the d theta at the top of a fraction before. Who thinks that looks really ugly? Like everyone, right? It's okay. I'm going to move it down. I hate it too. So this will become a d theta here. In the denominator, we'll have, that's going to turn into, we'll have 2 times cosine of theta. We'll have 4 cosine of theta d theta. Uh-oh. Something about that doesn't look right. Oh yeah. This should give us the integral of 0 to 2 of 2 d theta. So just 4, I think. I'm not sure. I didn't finish this problem before doing this one, but it should look something like that. Verify, exercise for you guys. Verify that that's correct. Yeah, question? Oh, I did, yeah. I said that out loud, didn't I? And then I didn't change the bounds. My mistake. So when x is equal to, we have arc sine, we have theta is equal to arc sine of x over 2. So when x is equal to 0, that whole thing will still be 0. When x is equal to 2, then we have the arc sine of 1, which is pi over 2. 0 to pi over 2, 0 to pi over 2. So we'll get 2 pi over 2, so just pi. Yeah, just pi. Okay, good stuff. Do we have any questions about anything that we've done today? Partial fractions or trig substitutions or arc length? If not, so let's get into some last minute announcements before we end. So we may have an exam review session. I'm not sure about that yet. I have to talk to Zara, we'll have to talk to the rest of the teaching team, see if we end up getting something, but we'll post about it if there ends up being one. Let's keep looking. There's the study sheet. Okay, if you haven't seen on Avenue, there should be a study sheet in the weeks 6 to 9 in the content section. So please take a look at that. Other than that, thank you guys for a wonderful semester. You guys have been one of the best classes I've ever had. Thank you all so much for a wonderful experience. There are candy canes all around the room. Please make sure you grab one before you leave. And also, please, if you get a chance, please fill out the feedback form. It really helps. I'll be here for the next couple minutes to answer some questions, so feel free to come by. Thanks so much, everyone.